Hello everyone. So starting from today, we will have the pleasure to follow the mini course by Professor Shirikan. Professor Shirikan will visit us for 10 days. He will give a talk for 4 times. And meanwhile, he has an office in W904. So if you have some questions to him, come to us. Or discuss some problem. Professor Shirikan has completed his PhD at Moscow State University. Then he had a junior researcher position at the Institute of Mechanics of Moscow. Then he moved to Edinburgh and held their research associate position at Harvard University. Then after 4 years, he moved to Paris University as a lecturer, and then was promoted to full professor at the Sergi Paris University. So he's known for his very deep result in stochastic PDEs and control theory. He is the author with Sergei Kuxin of a book, Mathematics of 2D Turbulence, which is one of the most influential references in the recent years. So Professor Shirikan will speak about, will present this mini course about the introduction to the Donsker-Varadhan theory of large deviations. Thank you.
Very much for the introduction. It's a big pleasure and privilege for me to deliver this course, and I thank the institution, in particular Professor Shirikan, for the invitation and hospitality. As mentioned, I will be talking about large deviations. So today's lecture will be more introductory, and will give some generalities on large deviations. Let me just ask, can everybody see it, or I should write bigger? Is it okay? Okay, so I will be giving 2 examples. 2 examples. Which will tell us what this course will be about. Well, the first one is Laplace type asymptotics. Let us consider 2 functions, f and g, which are defined on some closed interval AE with range in R, and initially I assume that G is greater than 0 everywhere. Then you have the following relation. If I take the limit as n goes to infinity, 1 over n integral logarithm integral from a to b exponential n f of x g of x dx. Then the claim is that this quantity, so I took this integral, because g is positive, this is a positive quantity, I took the logarithm 1 over n, and the claim is that this will converge to the maximum of the function f on the interval a. Well, let us prove this result. Proof is not difficult. So let's denote this quantity by an, not writing it every time, and this one by n. Well, the proof is split into 2 parts, upper bound and lower bound. So let me begin with the upper bound. Because my function f is smaller than n, I can write that an is smaller than, so let us replace a by its maximum value n, then I will have exponential m times n, an integral from a to b g dx. So this is a positive number because I assume that factor g is positive everywhere. And I can derive from here that 1 over n logarithm an is not greater than, when I take the logarithm and divide by n, I obtain n here, n plus 1 over n logarithm of c. And of course, this implies immediately that the upper limit when n goes to infinity of 1 over n logarithm an is not bigger than n. Now what about the lower bound? Because my function f is continuous, if I fix epsilon, then I can choose an interval j epsilon included in AB such that f of x will be greater than m minus epsilon for any x in the interval j epsilon. Right? Because n is the maximum of the continuous function f on a small interval, I will be able to have this lower bound for the function f. Then this implies that an will be greater. Now this function g is positive. I minorize this quantity by replacing f by m minus epsilon. So I will get exponential m minus epsilon times n, and then integral over j epsilon g dx. Again, this quantity is positive because I assume that the function g is everywhere positive. So this depends on epsilon, c epsilon, but it's strictly positive. Then this implies that lower limit when n goes to infinity of 1 over n logarithm an can be minorized by, I take logarithm, I obtain m minus epsilon n, I divide by n, it gives me m minus epsilon. And then this is a constant, and then I need to take the limit plus the limit as n goes to infinity. I will have 1 over n and logarithm c epsilon, which is a positive number. And obviously, this is equal to m minus epsilon. Right? So I wanted to prove this in relation 1. I had this upper bound 2. And now I have also this lower bound, right? So this lower bound 3. Upper bound is smaller than n, lower bound is greater than m minus epsilon for any epsilon. So if I combine these two bounds, I will immediately get the asymptotic relation 1. Well, this completes the proof. Now, one can consider a slightly more general situation, replacing the function g by a sequence of functions gn. So let's assume that now my quantity an is given by integral from a to b exponential n f of x, and now I have gn of x dx. And concerning this gn, I will assume that it has the following asymptotic representation. I have an exponential minus n, a function I of x, and then a constant which will be positive, plus a quantity which goes to 0 uniformly in x. So this small of 1, it is the asymptotics with respect to n. This goes to 0, uniformly in x. In the interval AB. And concerning the function I assume that it is a continuous function on the interval a. Well, you can interpret this as a measure on the interval AB. So I assume that this measure will end as a density Gn, and this density Gn obeys the following asymptotic representation. Then exactly the same argument as before allows you to show that if I take the same quantity, the limit as n goes to infinity, 1 over n logarithm an, then this will be equal to the maximum on the interval AB of my function n as before, minus this function I, which characterizes the behavior of this measure with n as n goes to infinity. So in particular, if this function I is positive, then this function Gn will go to 0. So the measure disappears on the set when I is positive, and it concentrates on the set when I is negative or 0. So this mu n has some concentration property as a sequence of measure, and this asymptotic relation characterizes how it influences the behavior of this Laplace type integral. Well, large deviation theory is about this type of asymptotics for infinite dimensional spaces, for measures of infinite dimensional spaces. Well, as an introduction, let's consider another example, which can be calculated exactly, which is still in finite dimension, but still very structured. So let us consider a sequence psi n of independent identically distributed random variables which have normal law, which means that the law of psi n is the Gaussian measure on R with 0 mean value and variance sigma squared, which is assumed to be positive. Just to be sure that everybody follows, let me remind you that this means the following. If I want to calculate the probability that psi n belongs to set gamma, then I need to do the following. This measure is the measure given by a density, and it has the following form: 2 pi sigma integral over gamma exponential minus x squared divided by 2 sigma squared dx. So this is the property that all the random variables are normally distributed with mean value 0 and variance sigma squared. And I consider the following property. I take the time average of these random variables psi n. I consider Sn, which is 1 over n, the sum k from 1 to n psi k. The goal is to understand what is the asymptotic behavior of the law of this random variable Sn. So, but this is not very difficult to calculate because I have a sum of independent Gaussian random variables. If I take the sum psi k from 1 to n, then the sum of independent Gaussian random variables is again Gaussian. And to calculate the mean value, I need to take the sum of the mean values, it is 0. And to calculate the variance, I need to take the sum of the variances, which gives you n sigma squared. When I now divide by n, the law of Sn, this variance should be divided by n squared. This gives you normal law with variance n minus 1 sigma squared. And therefore, I can write that probability that Sn belongs to gamma. Let's assume that gamma is an interval. Is an interval. what it gives. I have an explicit formula for the low. I need to take this formula in which sigma squared should be replaced by a minus 1 sigma squared. So it gives you square root of n divided by square root of 2 pi sigma integral over the interval gamma exponential minus x squared divided by 2 sigma squared, but I need to replace sigma squared divided by n, then the ratio of n here, dx. And you get exactly the same type of formula as here, because this one, you don't see it in the logarithmic scale. When I take the logarithm and divide by n, this term will disappear, and what you have here is exactly this relation, or the other one. So what you get is the following: 1 over n logarithm probability that Sn belongs to gamma is equal, can be calculated exactly, and you need to take exactly the same formula. So you need to take the maximum of what you see in front of n. So it can be written as maximum when x belongs to gamma of minus x squared divided by 2 sigma squared, or I can write it also differently. I can write it minus the infimum or the minimum, because of the continuous function. The minimum when x is in gamma of I of x, where I of x is exactly that function. Minus, there's no minus, x squared divided by 2 sigma squared. Sorry, I forgot the limit. So the limit of the probability that Sn belongs to gamma on this logarithmic scale, which means I take the logarithm and divide by n, can be calculated explicitly, and it follows from the previous example and gives you exactly this formula for the limit. So our goal is to get these type of formulas for measures on infinite dimensional spaces. And Dawes-Carmichael theory is about this type of asymptotics in the particular case of Markov processes. So I will go now to the next point, which concern the definition and basic properties of LDPs. Definition and basic properties. Well, if a polar will be known by x, this calligraphic x, a Polish space. It means that x is a complete and separable metric space. And when I have a Polish space and I want to consider measure of it, I will always assume that it is defined on the Borel sigma algebra. The Borel sigma algebra is the minimal sigma algebra containing the open sets. Minimal sigma algebra containing open sets. Now, before giving the main definition, let me remind you the concept of lower semi-continuous function. So definition, let I be a function of x. Now, I will always assume that it is a function from 0 to plus infinity is not excluded. And I will say that I is lower semi-continuous. In short, I will write L as C. So by definition, this means that for any x in x, the whole lower limit as y goes to x of I of y is minorized by I of x. Okay, so this is concept of lower semi-continuity. If I take the lower limit I of y when y goes to x, then I will not get anything smaller than I of x. When you have also upper semi-continuity, which is lim sum of I of y is smaller than I of x, then you have continuity. So for the theory of large deviations, it is the law of semi-continuity which is well adapted. And now the main definition. Let us consider sequence psi n of random variables of x-valued random variables. Okay, so which means that we assume that they are defined on some probability space, and this random variable takes values on in the space x. Now we say that psi n satisfies the large deviation principle, LDP, large deviation principle, if there is a lower semi-continuous function I from x to 0 plus infinity, such that if I take any set gamma in the Borel sigma algebra, then we can write the following. The limit, lower limit, as n goes to infinity, of exactly the same type, so 1 over n logarithm probability psi n belongs to gamma. Now the lower limit is always smaller than the upper limit. One over n logarithm probability that psi n belongs to gamma. So for the one I didn't write anything. Now the upper limit is smaller than minus I of gamma bar, and lower limit is greater than minus I of gamma dot, where well gamma bar or gamma dot is the closure interior of gamma, and if you have a set A in X, then I write I of A to denote the infimum of I of X when X belongs to A. Okay, so this is the main definition. Before going further, let us analyze with this definition. First of all, remarks. Let me write that side. Remarks. Well, the first one. So let's denote this relation 1, 2, 3, 4. Relation 4 is equivalent to the following two relations.
I'm sorry.
Yeah.
If gamma has no interior, then you define it as 0. Or...
Yeah, good question. By definition, I of empty set is equal to plus infinity, which means that if you don't have interior here, then you have plus infinity, minus will be minus infinity. So in that case, the lower bound is empty. There's nothing in the lower bound. Thank you. Okay, so 4 is equivalent to the following two relations, two inequalities. For any j open, you have the lower bound in when n goes to infinity, 1 over n logarithmic probability psi n is in G. And this is minorized by minus I of G. And for any f closed, leave the upper limit in soup as n goes to infinity, 1 over n logarithmic probability psi n in f is smaller than I of f. Now, this is almost obvious because gamma is included in its closure and contains the interior. So this is open and this is closed. So if you have these two relations, then you will have the range from 4 and vice versa. Taking here closed set gamma, you get the first relation, and taking here open set G, you get the second relation. Okay, so having 4 or having these two relations is the same. And for the rest, I will use the following notation. I will write that 1 over n, the limit 1 over n logarithmic probability psi n belongs to gamma is equal to the dot minus I of gamma, to say that I have exactly relation 4. So this is just the definition. So when I write this type of equality, not write every time mean soup or local mean for closed and so on, I will write this, meaning that you have these two relations or relation 4, which are true. So this is just a notation. Equality with a dot means that these two relations are true. Now, second remark, there is a case when I calculated on gamma bar and I calculated on gamma dot is the same. So if gamma is such that I of gamma dot is equal to I of gamma bar, and in that case it will be equal to I of gamma, because obviously I is a monotone function of the set. The bigger the set, the smaller I calculated on that set. So if you have this equality, then you have also this one. Then this upper and lower limit can be replaced by the limit. N goes to infinity, 1 over n logarithmic probability that psi n belongs to gamma, and this will be equal to minus I of gamma. Again, so it's very easy to see comparing these two quantities. So if this quantity is equal to this one, then the upper and lower limit can be replaced by the limit as n goes to infinity. Well, there are some other properties which I will not really need, but they are important to understand the theory of large deviations, so I will give it as an exercise. Exercise 1. Well, here in the definition of large deviation, I impose that this function I should be lower semi-continuous. The natural question is, but what if you have relation inequality score with a function I, which is not lower semi-continuous? And the exercise 1 gives an answer. So if psi n is such that for holds with a function j, which is defined on x with values on 0 plus infinity, then psi n satisfies LDP with I, which is defined in terms of j. So this is ln in, and y goes to x j of y. In j of y. Yes, so I said that psi n satisfies version 4, in which I is replaced by a function j, which has no lower semi-continuity property. Then the claim is that then 4 is also true with the function I, which is the low limit, which is defined in terms of j as the low limit of j of y when y goes to x. And in addition, I is lower semi-continuous. Okay, so if you have just relation 4, if you have relation 4 with just the function j, then you have the same relation with the lower semi-continuous function I. So imposing lower semi-continuity is not a restriction of generality. You can always assume that the rate function, yeah, sorry, I forgot to say that this function I is called rate function. So I is called rate function. This is the definition of rate function governing the LDP. Now second exercise, again related to the rate function. The natural question is if you have LDP with two different rate functions, the answer is no. Exercise 2. Prove that the rate function is unique. In fact, it can be expressed in terms of the limits, upper and lower limits. Okay, so I will not go into details of the solutions because they are not needed in this course. Now, let us consider an example, a trivial one. Let us suppose that our space X is just a finite set with a discrete topology, X1, Xn, and I need to define metric space because X is a complete set of metric space. Then the distance on this metric space is just 0 or 1. It is 0 when the point coincide, and it is equal to 1 when the points are different. So let us consider psi n, the sequence of x rated random variables. Well, the example is trivial, but still it is useful to understand what it means that this sequence satisfies the property of our deviations. So LDP, the claim is that LDP for psi n with the rate function I, well now the rate function any function here is over semi-continuous because it is discrete topology. This is the same as the following. For any j between 1 and n, you must have the following. So this is discrete topology. All the sets are closed and open. Therefore, you have equality. And trivial remark is that you will have that if you have this relation for singletons. Limit 1 over n lowering probability that psi n is equal to a j. Is equal to minus I of aj. And it's really easy to understand that in the case of finite set, because all the sets are simultaneously open and closed, you can apply this remark, because all these three sets are the same, and then you have equality for any gamma, and then because again everything is finite, it's not difficult to understand that if you have this relation when gamma is a singleton, then you will have this relation when gamma is arbitrary subset. Okay, let us consider examples. Let us consider more interesting examples. And this is the goal of this course. At the end of this course, we'll be able to prove our relations for the following example. So let us consider ordinary differential equation in random coefficients. Ordinary differential equation with random coefficients. What it means is the following. I have n plus 1 vector fields on RB. And I consider the following equation. X dot is equal to V naught of x plus the sum j from 1 to n into j of t v j of x. Okay, so if I consider this is just ordinary differential equation. If I consider eta j vj, so I need to specify who is eta j. So eta j are random functions, random processes from R to R. And to ensure that the solution is well defined, I assume that trajectories are smooth. Smooth trajectories. Okay, so when you have a random process with smooth trajectories, for any realization of the random process, you can construct a solution. So you get, if you specify the initial condition, it's not equal to x naught, then you can construct a solution. Well, one can construct a solution. Xt. Of course, you need some conditions to make sure that this solution is globally defined. For instance, you can assume that V naught, Vm are globally Lipschitz continuous, then all the solutions are defined for T in R. So we need to not specify these conditions for the moment. And then you can have the following two examples for which you can construct, you can ask the question about the limit of our relations. The first one, let us consider bounded continuous function from RB to R. And given this function, I can consider the following sequence of random variables. This is the time average of the observations of solutions using this function f. 1 over n, the sum k from 1 to to n f of xk. So xk is the value of the solution at time k. So this is a random variable because my solution is random. Then I observe my solution using f. So I have some real valued random variables, and I take the sum time average. So this is exactly the quantities which are interesting when you study the large behavior of trajectories from a stochastic point of view. You cannot expect a limit for every individual trajectory, but if you take the time average, then you may go to have a meaningful limit. So this is a sequence of real valued random variables, and you can ask the question if large deviation principle is true for this sequence. So this example is very similar to the one considered there. In that example, I assume that random variables psi k are Gaussian. Now there is no reason for this random variable to be Gaussian and independent. They are not independent. And you can ask the question if you have the LDP for this sequence. Another example, which is even more interesting and more general, is the following. Let us consider the following sequence of measures un, which is 1 over n, the sum k from 1 to n, and I take the Dirac mass of the point k. So here, so this measures have name, they are called empirical measures. Empirical measures. Also called occupation measures. So here, delta y is the Dirac mass of y, which means that delta y calculated on set gamma is equal to 0 when y is not in gamma, and 1 when y is in gamma. So I take Dirac mass at a random point xk. So for each realization, for each omega, this will be the sum of Dirac masses divided by n. So this normalizes. So this will be probability measure on RB. But because our trajectory is random, you have a random variables. So psi n, mu n is a random variable with values in what I denote E or D. So by definition, this is Borel probability measures on RB. Now, of course, you may have the question, why it is a metric space? So this is a important question. We'll discuss it a bit later. For the moment, let's assume that this is a indeed metric space. So you can consider the space of measures, Borel probability measures, on this space. So in the to relate this object with the previous one, with the theory of large deviation, so this will be our space X. Right, so you have a argued object, you have a measure, we have a random variable, which takes values in the space of measures. So for each realization is the measure. In particular, the law of mu n will be measured on the space of measures. You may need some time to get used to that, but this is a really natural object in the theory, in the non-scalar theory. So this may be subtle point, so let me repeat once again. So you have a trajectory, you take Dirac mass, the point xk. So this is a measure on RT for any realization, but because xk is random, you have a random Dirac mass. Then you take the normalized sum, so you still have a probability measure. So this is an element of P RT, but because xk depends on omega, it is a realization of my solution of this equation, which has randomness here. So you get a random measure on the space RD. And then you can ask the question about large deviations. If this sequence of measures satisfies the large deviation principle with some lowest and continuous function I. Well, there is a relation between these two examples. So given a function f, so if I have a function f, which is a bounded continuous function on Rd, I can consider phi f, which will be a map from the space of probability measures into R, and it takes any measure u to the integral of f with respect to me. So this is integral over Rd f of x u of the x. Right? So you have a function which acts on the space of measures with range R, and it takes any continuous function or any continuous observable to its mean value with respect to this measure u. Sorry, f is fixed. It's in this formula mu is variable. So f pf phi mu is just the mean value of this function f, which is fixed with respect to this measure mu. And then it's easy to understand that if I take this function and apply to mu n, we're going to do it. Phi f applied to mu n by definition. So this is definition, right? Duality between measures and functions. F mu n. I need to integrate the function f with respect to the sum. So I have 1 over n f the sum of their classes. But then integrating the function with respect to their classes is very easy. You just need to take the value of f, which is at the point xk. So what you get is 1 over n, and the sum k from 1 to n f of xk. And this is exactly my variable psi n. Right, so this will be our main goal, to find conditions of eta j such that trajectories of this orbital differential equation with random vector field satisfy the large deviation principle. Okay, so let me summarize. So we introduced the concept of large deviations. This concept of large deviation can be written in different forms. It can be written as two bounds, one upper bound and one lower bound for all and dual sets. There are some interesting cases when you have a limit. It is the case when the rate function calculated on the corner and interior is the same, and it is the situation there. This rate function I of x, calculated on the corner of interval, for the interior of interval is the same, because it is continuous and you have just two additional points. So what is written here is nothing else but the large deviation principle for the sequence Sn, which is the time average of the sum of independent Gaussian random variables, independent identically distributed Gaussian random variables. Well, I think that's it concerning definition. Now I prove two properties.
One question.
Sure.
The large deviations refers to the distance between those two limits, usually, or
The large deviation is in fact well, there is what's called central theorem, which says that if instead of dividing by 1 over n, you divide by 1 over square root of n, then you have some particular limit. And you can rewrite central limit theorem as the probabilities of deviations of order 1 over square root of n from the mean value. Right now, So the central limit theorem describes the deviation of the time average of random variables from the mean value, which are accorded 1 over square root of n. The large deviation describes deviation from the mean value of order 1. So it is large with respect to 1 over n. So maybe the term is not very intuitive, but it is what is called. How it's called. Okay, so let us prove two properties. And from now on, to simplify things, and because this will be our main example here is given on RD, but in the final step, and I will prove it, I will deal with ordinary differential equations on a compact manifold, and then everything will be compact. From now on, I assume that X is not only separable, but also compact. Compact metric space. Okay, so everything what is said here can be applied in a compact case. So I will assume from now on that X is a compact space. Then the first problem, the first result theorem, it is called contraction principle. Well, it has nothing to do with the bound theorem on contraction mapping, on contractions. It says that if you have a sequence that satisfies LDP, if you have a continuous map from one space, from your space X into another space Y, then the image will also satisfy the Law deviation principle. So here's the exact formulation. Let psi n be a sequence satisfying let me specify sequence of X value random variables satisfying LDP with an array function I. So can I just be I goes from X to 0 plus infinity, and let phi be a continuous map. And so X value random variables, and you have a continuous map from X to Y. Now, because X is continuous, X is compact, the image of X by phi will also be compact, so I can assume without loss of generality that Y is also compact, so they are still in this framework of compact phase space. So the conclusion is then f of psi n satisfies LDP with the contracted rate function given by the following formula: J of Y is equal to the infimum of I of X, where the infimum is taken for all pages over all X for which Y of X is equal to Y, and as usual, infimum or an empty set is equal to plus infinity. This is a simple result, I will prove it. I think it will be very useful for us.
Here the I's are two different, the capital I is J.
The other one is, this one is J. This one is I.
Okay.
Phi, sorry. This is phi of psi n.
It maps X to Y, so as the any definition for
This is X. Yeah, I didn't specify Y in another vector space. And there is a function phi. So your own variable takes values here, psi n is here, and phi of psi n will be here. So phi of psi n is a sequence of wide range of random variables. And if LDP is proof of psi n, then LDP is proof of phi of psi n, and the rate function can be written explicitly. Okay. Now let's prove it. Well, usually when you prove our relation, very often the proof splits into two parts, exactly as in those examples. In the first one, Laplace asymptotic, we have upper bound and lower bound. Very often this will be the case more difficult example. So let's begin, for instance, with upper bound. Now, upper bound, by upper bound, I mean the second relation there. Right? When we have closed, we need to have this. But it's faster to write the definition. So 1 over n, the upper limit, probability that phi of psi n belongs to a closed set F, and n goes to infinity. Now this is the same. Let me write limits. Sorry, the upper limit. So upper limit, then n goes to infinity, 1 over n, lower probability. This is the same as the upper limit. As n goes to infinity, 1 over n, lower it, probability that psi n belongs to phi minus 1 of f. But n is closed, phi minus 1 of s is closed, so this is closed set. And therefore, by the large deviation principle for psi n, this limit, this upper limit, is not bigger than minus I calculated on phi minus 1 of f. So it remains writing phi with phi minus 1 of f, I phi minus 1 of f. I phi minus 1 on n is at a. So this is the infimum of I of x when x belongs to phi minus 1 of a. Right? But phi minus 1 of a can be written as, so this is infimum over the I of x such that phi of x belongs to a. Right? So I didn't change anything. I'm taking the infimum over all x such that phi of x belongs to a. So this can be written differently. I can first take the infimum when y belongs to a, and then infimum over all x such that phi of x is equal to y. Right? So if you have infimum of infimum, it is the same as the infimum taken at once. And then I use the fact that these two infimum commutes, in contrast to sup inf or inf sup, when you take twice infimum of twice infimum, you can commute them. Then what you get is the no, sorry, you don't have commutation, it's just what is written here is just j of y. infimum y in A of j of y, because j of y is exactly this, infimum phi of x phi x equal to y. And this is j of A. So what you got here, from here, you get me see that this is equal to minus j of x. And this completes the proof of other bounds, and low bound is the same. Okay, so the proof is essentially trivial, but then there's something not trivial. It just pretend that I phi minus 1 of A is exactly j of A. Okay. So this shows the contraction principle. So it says that if science satisfies the observation principle, then the image also satisfies the observation principle. Obviously, the converse is not true. So it's easy to construct an example when psi n does not satisfy, but phi of psi n satisfies the observation. For instance, let's take any example which does not satisfy the obligations. Psi n any sequence of random variables. And then you take phi from x to y such that for any x, phi of x is just given point and y hat. This is a given point in x. In y. And so what you have is just constant value variables.
What would be the simplest example of such a sequence not satisfying?
You take Bernoulli 0, 1, and it will not satisfy. You take the sum without normalizing, it will not satisfy. Okay, so I mean, most sequences do not satisfy principle aggregation principle. Just take any sequence of random variables which are maybe you can even take independent, but without any normalization condition, then it most likely will not satisfy.
Yeah. How about your example in the finite and the discrete case? Is it
This should be 1 minus delta ij, right?
Sorry?
Example 1.
Example 1 there.
Distance 1 minus delta, right? Or what is the definition of that?
Well, delta ij is 1 when I is equal to is different from j, maybe 1.
Distance,
So distance is 0 when they are just sorry, yeah. 1 minus delta ij. 1 minus delta ij indeed. So if I is equal to j, then this is 1, it should be 0. Thank you.
and in this case there is always a large deviation, or also it can happen mostly that it is not having a large deviation?
No, it's no, it will, I mean, what is always true, if I will talk about it later, that you can always extract a sequence which is sign combinations. But here again, take 2 points and just take what you can take. But anyway, so it's something.
So this discrete case is similarly difficult than the non-discrete, or like there are also counterexamples for the discrete case.
No, there are counterexamples in this case. I mean, it's Yeah, yeah, so I think that's the one. Okay, so then we have a constant sequence, and this constant sequence always satisfies our variation principle. So phi of psi n satisfies LDP with a rate function I, which is equal to 0 when y is equal to y hat, and plus infinity when y is different from y hat. Yeah, concerning your question, I mean, you take random variables, which is you just alternate between 2 points, and the limit cannot exist. Okay, psi 1 is equal to x1 with probability 1, psi 2 is equal to x2 with probability 1, and so on. Well, so the fact that you have large deviation for the image does not imply that psi n satisfies large deviation. So what is one of the key points of this course is that if you have sufficiently many, if you have a sufficiently large family of functions phi for which you have large deviations, then psi n will also satisfy large deviations. And the first step in doing that is what is called Vara lemma. So there is the second result. Theorem, it is called Vara lemma. And it says the following. Let psi n be a sequence of x valued random variables satisfying LDP with a rate function phi, rate function I. It goes from x to 0 plus infinity. And let f be a continuous function. Then you have the following. Well, the example was under here. The limit as n goes to infinity, 1 over n logarithm mean value. So now I take the mean value rather than of exponential of phi of psi n. Then this is equal to supremum when x belongs to x of f of x minus I of x. Okay, let's try to see what is the link between this formula and what we had before. So this relation, let's see, if phi was already there, let's write here 6. So 6 can be written in the following form. 6 is the same as the limit as n goes to infinity, 1 over n logarithm, and here using the expression for this mean value in terms of the log of random variable psi n, I can write it as an integral over x exponential, sorry, it will go n here. There's n here, n f of psi n. And here I can write here n f of x, and I need to integrate with respect to measure mu n. Mu n is the law of psi n, which means that mu n of gamma is just the probability that psi n belongs to gamma. So what is written here, the mean value of exponential n f of psi n is exactly this integral. And this integral is a generalization of what we considered in the beginning of this lecture. So integral exponential of n fx multiplied by a measure mu n. In our example, mu n had a density, which had some particular property of asymptotic property expressed in terms of the function I. Now we are on a space X, which is just a general compact space, don't have any reference measure, but still we can define some asymptotic behavior, and it is defined in the definition of our deviations. So mu n, if this sequence of psi n satisfies the deviation principle, then this integral, which is similar to the one considered before, can be calculated by exactly the same formula. So this is the supremum of f of x minus I of x. The supremum is taken over xx. Okay, so this comes out of that. Now let us see where this formula comes from. And for that one, I will again consider the trivial example we studied there, when you had only finite many points. And in this case, our deviation was exactly this relation. Our deviation here is this one. And we'll try to see why this implies immediately what other way in this particular case. For example. So x is equal to xn, x1, xn. So let's calculate the mean value of exponential n f of psi n. So we have a finite state space. So this is the sum k from 1 to n. I did not have the index j, so we can write j here. J from 1 to n. I have exponential n of f of xj and the probability that psi n is equal to xj. But psi n equal to xj has some precise asymptotics. This behaves as exponential minus I of xj multiplied by n. So I can write this as the sum j from 1 to n exponential n f of xj minus I of xj, and then I have a correction which is a small o of 1, which is a quantity which goes to 0. Now what I need to do is to take the logarithm and divide by n. So 1 over n logarithm mean value exponential n of f of psi n. The claim is that if you are studying the sum of exponential functions, if you take the logarithm, then the biggest function will win. So this will behave as I take the logarithm and I divide by n. So this n will disappear and I will have these functions. But since this logarithm I cannot put the logarithm here, so logarithms stay outside the sum, the biggest logarithm will win. So this will be maximum f of xj minus I of xj, j between 1 and n, and this is true when n goes to plus infinity. So this quantity behaves like this, and this is exactly the quantity you have here. Well, I think I will not have time to give the proof, but the proof is essentially made from this argument. You just need to cut your phase space into small pieces. Again, the proof is divided into two parts, upper bound and lower bound. So you cut your space, your free space is compact. Basically, you cover it by small balls. On this small ball, you apply large deviation principle, and you get easily up and low ground. So this is really, really soft result. So I will skip the proof for the moment. Let's see what it gives. So let us consider an example which will be very important for us. Let us consider a space X, which is compact metric space. Now, I really insist that this X is different from the X before. Because what I want to consider is the following. So I consider the space Cx, which is the space of bounded continuous functions on X. Then the next object is the dual space. It is the functionals linear continuous functionals. And there is a well-known result called Rees-Markov theorem, which says that this is exactly the space of sign measures on S. Finite sign measures on S. Well, this space is separable. This one is not, in general. For instance, if you take X equal to 0, 1, the simplest possible case, then Mx is not separable. Therefore, if I take the second dual of this one, well, when I make Mx, so this is space, this is the dual space of Cx, there is a natural metric on it, right? You need to take the supremum on the ball of radius 1. So this space Mx with that metric, which is called total variation metric, is not separable. Therefore, the dual of this one cannot be C of x, because the dual of a non-separable space cannot be separable. But there is another metric which is more adapted to our purposes. It is a weak star topology. So definition: weak star topology on Mx. So this is the topology generated by sets of the form. So I take u, it depends on a measure mu, so this will be the element of M of x. It depends on a function v, and depends on number epsilon. So this is the space of all mu primes in Mx, such that if I integrate v with respect to mu prime and v with respect to mu, then the difference is smaller than epsilon. So in other words, the topology of Mx is the topology of convergence on continuous functions. So the sequence mu n converges to mu in big star if and only if for any v mu n converges to v mu. And just if you think 5 minutes about this topology, we'll easily get this result. So the topology is the minimal topology containing all these sets. The sets depends on mu, v, and epsilon. So this set is the set of those measures, mu prime, for which the integral with respect to mu prime is different, minus the integral of v with respect to mu is no greater than epsilon. So this defines the generated family for the topology. So big star topology on Mx, which is much bigger than the natural topology on the space Mx, is characterized by this property. So mu n sequence converges to mu in the big star topology if and only if the integrals converge. And a non-trivial fact is that if you take this Mx with big topology and you consider the dual of this one, then what you get is exactly C of x. Now, this is a non-trivial result. Well, it follows from what is called Goldstein theorem, but I have no time. It is a consequence of Goldstein theorem. I have no time to discuss it today, at least. But this is important for us just to have a triple Cx dual of this one and dual of this one with big star topology again of Cx. And here is why. So let's try to use. Let us suppose that in Varana lemma, so this should be the main example we should keep in mind. So in this example, what we are interested in is the space X, which will be P of X, which is a subset in M of X, and I will consider this with big star topology. Okay, so our space, this is P of X. And P of X is the space of probability measures of X. It is a subset, it is not subset, it is a subset in the space Mx. And this is a compact subset due to Prokhorov theorem. This compact. And this is Prokhorov theorem. Now, let us consider a bit more general situation. Let us take any space, any compact space X. Now, let's assume that this X is a compact subset in a topological vector space. Well, in our example, this topological vector space will be exactly this one, Mx with big star topology. So this is no longer a vector space. This one is a topological vector space. Big vectors cannot be vectorized here, though it can be vectorized here, but this is not important for the moment. So let's assume that this X is included in this topological vector space. Now let's apply this formula in the particular case when f is just a linear function. E belongs to dual space of E prime. And the dual space of E prime, in this example, will be exactly this one, C of X. Now let's see what it gives. Relation 6 implies that the limit when n goes to infinity, 1 over n logarithm mean value exponential n. Now I need to take p applied to psi n, right? Because I have a topological vector space. I take a continuous function of this topological vector space. So this will be a continuous function. I have the right to apply this formula. Of course, this one will not be bounded in here. I assume that this continuous, this continuous on a compact set. This set is not compact, but I consider my function restricted to this P of x, which is a compact subset. So if I apply formula this formula to Varda formula to this particular case, then what I get is the supremum when x is in x. Instead of fx, I should write px and minus I of x. Okay, so let's denote this by q of p. So the Varda lemma says that this function q of p is well defined and is given by this formula. Now, an exercise is that this function q is convex it is a convex function, and sorry, this function is convex. So Varda lemma says that this convex function q of p can be written in this form, but this quantity has a name. What is written here is the Legendre transform of I. So according to Varda lemma, if psi satisfies our deviation principle, and if this space X is a subset of a topological vector space, then this quantity has a limit as n goes to infinity, and it coincides with the Legendre transform of phi. I is not necessarily convex, but if, so important remark, if I is convex function, then a well-known property of Legendre transform says that you can recover the function I, the convex one, from its Legendre transform. So I of x can be written as a supremum of px minus q of p, and p belongs to p prime. I can guess that some of you may feel a bit confused about all this stuff, because there was quite a amount of information about this. But what is important is that Varda lemma, applied to this particular case, gives you a candidate for the rank function governing our deviation principle. So in Varda lemma, you apply it to this particular type of functionals. You get q of p, which is always well defined, and it's a convex function. It can be written as a Legendre transform of this function, and this quantity is always well defined. You take the supreme of something. Then the theorem of convex function says that if this function is also convex, in general it's not true. You can have large deviations without convexity, but if this is also convex, then necessarily it should be given by the Legendre transform of the function q. So I think I will stop here. So the next lecture will be some further. I begin the next lecture with some analysis of this example applied to this theory, this result applied to this particular example. I think I stop here for today.
You have a question? So the large deviation principle we share here is about constant rather than time back. It's avoiding the so-called binary and pencil timeline difference.
Primary method is when you put here epsilon, and you want to study what happens with trajectories when epsilon goes to 0. So those curve down tells you run the asymptotic discontinuity, time average of observables calculated on solutions. Primary method tells you about the behavior of trajectories on finite intervals when this epsilon goes to 0. So in other words, you take the deterministic system and you perturb it by noise. So the question is what you get in the limit. So this noise usually regularizes your system. You properties which are not true for the deterministic one may be true for this one. For instance, you can have some regular behavior as time goes to infinity. Now the other properties. So primary method is about the asymptotics of solutions for this equation, maybe even with random initial conditions, when epsilon goes to 0. It is again large deviation type results. You have convergence. It's easy to see that you have convergence to the trajectories of this limiting equation. But the question is, what is the exact asymptotic of convergence? Okay, so what is the deviation from the limiting trajectory? What is the exact probability of deviation from the limiting trajectory? So I will not discuss primary method here. This will be about post-evaluation. Thanks.
Other questions? Is there a simple criterion for I being convex? So that something that case by case you have the most important situations.
No, there are important situations that are not convex. In this course and in the theory of the Oscar listing before it was created by Oscar Varnam, it's always convex. When it is not convex, it means that well, usually in theory, when it's not convex, it's much more difficult. I call this regular case, and in a regular case, it's always convex. And what I mean by regularity, I will discuss it. It is indeed calculated using the scheme.
Other questions? Okay, thank you very much.